So from the last video, we talked about specifically how you define functions when you're dividing them by each other. And I left off, and I want to make something a little bit more clear. When you define something that is a fractional function, when you divide two functions together, we had this for the quotient f of x over g of x. And we had the reciprocal of this for the second part of the question. Now, the part of the question that I want to reiterate and kind of explain to you is how you define what the domain for each one of these is. We talked about the domain for this as all non-negative numbers, or it could be 0 or above. I did some work over here, and it's not in this video, but we talked about them being from -2 to 2 as possible numbers you could plug in. But the problem for this is that you can't plug in all these numbers, because if you plug -2 in, you get 0. If you plug 2 in, you get 0. We can't have a 0 in the denominator. So as an inequality, we go from -2 to +2. Now here's the second part of this problem. We have two different sets of numbers that work for both the numerator and the denominator. How do you deal with that? Well, in terms of a number line, here's what we have. We have the numerator, which says we can use all of these numbers. And we have the denominator, which says I can use from -2 to +2 and everything in between, but not including those two. So how do I decide which ones I use for my domain? Well, if it's going to work for the function, it's got to work for both the numerator and the denominator. So I have to see where they have in common. So they start at 1, or excuse me, they start at 0 and they have 0 in common, and they appear to kind of have everything in common all the way up to 2, but they don't include 2. So what we would say is that the domain for this is from 0 all the way to 2, but not including 2. Every number from 0 all the way to 2 can work in this function. And that's your domain for this one. Now, in reverse, in the numerator, I can use -2 and +2. The reason is because I get a 0 in the numerator, it's okay. The problem is I can't have a 0 in the denominator, so I have to say that it can only be greater than 0. So looking at this from a graphing standpoint, I have from -2 to +2, and I have from 0 all the way over to +infinity, and keeps going on without stopping. So we have to ask ourselves, well, what numbers can we use here? Well, we can't use 0, but I can use everything to the right of 0 all the way to 2. So the domain for this is not including 0 all the way to 2. Now this is kind of a hard concept to grasp for one example, so I will be going through another one with you with this checkpoint. So make sure to look at this when we go through it. But I want to talk about another type of operation that you can deal with specific types of functions, and this is the idea of composition of functions. When you usually see functions, whatever they are, you're usually asked to say, well, what's this equal? What's this equal? Whatever. We've gone that far in this class. What we're going to do now is we're going to do a little bit different things with evaluating functions. When you compose functions, you are evaluating a function with another function. Okay, so I'll say that again. Instead of plugging in a number, you're plugging in an entire function. And you're going to see notation that looks like this in the book. It looks like the word fog, but what it actually means is I want to evaluate this function f and replace f with g of x. And you can see it kind of parallels with what I have written here. This is more appropriate notation to start with, just so you know what it looks like. So what I'm going to do is evaluate when x is equal to g of x. So I'm going to evaluate x in this equation with a function. So what does this look like? Well, I'm going to replace x with a function. So it's going to be g of x plus 2 instead of x plus 2. Now, I have to go a little bit further because we know what g of x is equal to. We know what that's defined as. So I'm going to replace that with 4 minus x squared plus 2. And to simplify this, combining like terms, I'm left with negative x squared plus 6. Okay? So, there's my function, and there's what it equals. Now I am asked to do the exact opposite. I'm taking g of x here, and I'm asked to evaluate it when it's f of x. So what I'm going to do is I'm going to replace x in g of x with f of x. I'll say that again. I'm replacing x in f of x with, let me say it, I'm replacing f of x with x in g of x. So wherever I see x here, I'm replacing that with f of x. So instead it's going to be 4 minus f of x squared, or 4 minus x plus 2 squared, which is equal to 4 minus, if I square all that out, I get x squared plus 4x plus 4. Combining like terms, I get the 4 and the minus of 4 cancel each other out. I'm left with negative x squared minus 4x. And there's my newly defined function replacing x in g of x with f of x. Now it's asking us in part C to replace x with a number. So we have this function defined. Now we're going to just plug in, like we've done before, a negative 2. So wherever I see negative or x in this function that I've defined, I'm going to replace it with a negative 2. So a negative 2 squared minus 4 times negative 2, which equals negative 4 plus 8, which equals a positive 4. Now there's an alternate way to do this, and I'm going to show you how you do this from a graphical standpoint in the book when we go through some of this in class. But this is how you define certain things, and this is how you evaluate them after you define them. So another thing we have to do is define specifically how you deal with a domain of a composite function. So it's asking us to deal with this operation. So I'm replacing x here with g of x. So if I'm defining this, that's the same thing as replacing x with g of x. So that's g of x squared minus 9, which is the square root of 9 minus x squared minus 9, which is equal to 9 minus x squared minus 9. These cancel out, and you would think that the final answer is negative x squared. That's what you get with a simplified composition. So this is equal to, after composing this, to negative x squared. The problem is that when you look at this newly defined function, not every value works. Well, you would think that with this type of function, which I'm going to now call h of x, that I could plug in any number that I want. And if this was the original function, we could. I could plug in any number I wanted to and get an answer back, but it's not. Okay? This is technically the original function. We just did some simplifying. So this is not the original. This is the original. So you have to go back and look at the original thing before you did any simplifying and ask, well, is there anything that we can't do? Well, we have a square root here, and you can't take the square root of a negative. Just because they cancel out doesn't mean you still can't, or you can take the square root of a negative. So when we did this earlier, we had 4 minus x squared. It was between negative 2 and positive 2. With this one, we're going to run into the issue of from 9, the square root of 9 minus x squared, it's going to be from -3 to +3 that we can plug numbers in. And that's the only restriction that you have for this. So your domain is that it can be from -3 to +3. And this is your domain for this. A lot of times people take a look at what you get after you simplify it and say, well, what's the domain of that? But what you really need to do is look at what really was done before you do any simplifying. The last problem that I'm going to look at for this video before I talk about the next part is how you decompose a specific composition function. So what we have is this function, and it was the result of taking two functions and plugging one in for x. Well, hopefully you can see that there was some sort of outside function to start this and that something got plugged in for x. And you can see here that if I take a look at this expression here, this could have been an x originally, okay? Could this originally have been an x? Yes. And if it was, it would have looked something like this. And before we did anything with it, that's what it possibly could have looked like. So this could have been my original function. Now, what would we have had to plug in for this to make this new function be written like this? Well, instead of x, we replaced that with x minus 2. So our two functions are 1 over x squared and x minus 2. Now this isn't the only set of answers. There could be a lot more different ones. Another one could have been 1 over x and x minus 2 squared. Those are two possible answers. Okay? But you have to ask yourself, what did we plug in? What could have been this outside structure of this function before we started messing around with it and started putting things in for x? And for the last part of the video, I'm going to talk about the application problem.